Hey everyone. So in this video, I'd like to cover some problems from the Midterm 2 review activity. So let's start with this example involving inverse trigonometric functions. Now remember that for trigonometric functions, y is equal to sine of x, y is equal to cosine of x, and y is equal to tangent of x. The inputs of these functions all represent angles. And the outputs of these functions represent coordinates or ratios of coordinates on the unit circle. So y coordinate is what sine gives us. The x coordinate on the unit circle is what cosine gives us. And then tangent gives us the ratio of the y coordinate divided by the x coordinate, and this can be viewed as the slope. And then inverse trig functions, well, they reverse this. And so sine inverse, it takes in inputs of y coordinates on the unit circle and returns or gives back angles. And this is similar for the other trigonometric inverse functions, right? So y is equal to cosine inverse of x and y is equal to tangent inverse of x. Here we've got inputs of the x coordinate and the slope. And these inverse trig functions again return angles. And so they don't just give back any angles. To make sure that they're functions, they return back angles in a specific interval. So inverse sine gives back angles between negative pi over 2 and pi over 2. Inverse cosine gives back angles between 0 and pi. And inverse tangent gives back angles between negative pi over 2 and pi over 2, not including these values. So pictorially, inverse tangent is only going to give you back angles on the right side of our unit circle between negative pi over 2 and pi over 2. Inverse cosine is going to give us back angles between 0 and pi, so angles along the top half of the unit circle between 0 and pi. And then inverse tangent is going to give us back angles between negative pi over 2 and pi over 2, but excluding the values negative pi over 2 and pi over 2 themselves. And so we don't have time to completely review why these are the choice of angles that the inverse trigonometric functions give back. But here, this is probably the most confusing part about inverse trigonometric functions, and so I definitely encourage you to remember these intervals for each of the trigonometric functions. I should say that on these intervals, each of the functions sine, cosine, and tangent do not repeat themselves, and so this is what makes the inverse functions truly functions, the choice of intervals here for which the inverse functions give back angles at. So let's use these ideas to evaluate some of the inverse trigonometric expressions on the left. So arc sine of negative 1/2. What this is saying is that we've got a y coordinate of negative 1/2 on our unit circle. What's the angle that sine takes to negative 1/2, but specifically the angle between negative pi over 2 and pi over 2. So let's draw this out on a unit circle. So here's my unit circle. And so here we're saying we've got a y coordinate, right? Inverse sine gives us y coordinates on the unit circle. So inverse sine of negative 1/2 is going to give us it's a y coordinate of negative 1/2. And we want to find the angle that gives us back such a y coordinate. So we've got an angle out here, and any angle out here, those are such angles that have a sine value of negative 1/2. But inverse sine only gives back angles between negative pi over 2 and pi over 2. So it's specifically going to be this angle here. Right, so here we've got a 30, 60, 90 triangle. This is negative pi over 6. That's what we get back from arc sine of negative 1/2. Is negative pi over 6. Okay, what about cosine inverse of negative 3 over 2. So here, negative square root of 3 over 2, this is an x coordinate on our unit circle. And so let me redraw out this picture. So we've got negative square root of 3 over 2 as an x coordinate on our unit circle. So that's about here. And so this is x is equal to negative square root of 3 over 2. And again, cosine inverse is going to give us back angles between 0 and pi, so only in this window here. So although there are two positions on our unit circle which give us a cosine value of negative square root of 3 over 2, well here cosine inverse is only going to give us back this one because it's the angle in the interval from 0 to pi. So this is 5 pi over 6, right? So here we've got a 30, 60, 90 triangle. This long leg length is negative square root of 3 over 2. So here this is 5 pi over 6. All right, now what about sine inverse of sine of 4 pi over 3? So you might guess that here we've got a function and its inverse composed together. You might guess that they will undo each other. Well, sine inverse is really only the inverse function to sine in the specified interval from negative pi over 2 to pi over 2. Outside of this interval, these functions do not undo each other. And so here, again, we can go through the motions. Right here, we can just sort of evaluate this from inside out. I always have trouble erasing little bits without erasing the entire thing. But maybe I won't bother. Okay, there we go. So here, let's evaluate from this this expression inside out. So here we've got sine inverse of sine of 4 pi over 3. So sine of 4 pi over 3, well, 4 pi over 3 is here, right? It's pi over 3 past pi. In other words, 60 degrees past 180 degrees. And now sine of 4 pi over 3, this is going to be the y coordinate on our unit circle at this particular point. This is negative square root of 3 over 2. So here really this amounts to evaluating sine inverse of negative, I'll use green here, negative square root of 3 over 2. Well, what's sine inverse of negative square root of 3 over 2? Here this is asking us what's the angle between negative pi over 2 and pi over 2, so on this right side of our unit circle, that has this y coordinate, negative square root of 3 over 2. Well, negative square root of 3 over 2 is the y coordinate drawn below. And so there are 2 points on our unit circle with such a y value. So here we've got any angle that comes out here on the right or any angle that comes out here on the left. But since sine inverse only gives back angles between negative pi over 2 and pi over 2, what we're going to get is this angle on the right. And this is going to be a 60-degree angle in the negative direction. And so this is going to give us negative pi over 3. This is equal to negative pi over 3. Okay, what about arc cosine of tangent of negative pi over 4? So I didn't mention this in this video, but arc cosine is the same as inverse cosine. These are just two different ways of saying the same thing. So my pen is having a little bit of trouble erasing. Give me one moment. Sorry, there we go. Okay, so here we want to evaluate arc cosine of tangent of negative pi over 4. Well, negative pi over 4 is this, it's this angle here. And if we really sketch out this line, right, tangent of negative pi over 4 is going to give us negative 1. This is a line with slope of negative 1. And we can really see that by noticing that here, this triangle is a 45, 45, 90 triangle with side lengths of square root of 2 over 2 and negative square root of 2 over 2. So when we take tangent of this angle, negative pi over 4, and we divide those two x and y coordinates, we just get negative 1. So here we've got arc cosine. I always forget the second c when I write arc cosine. Arc cosine of tangent of negative pi over 4. This is equal to, well, arc cosine of negative 1. And so arc cosine gives us, it takes in an x-coordinate on the unit circle, and it gives us back an angle between 0 and pi. So here this is an x-coordinate of negative 1. And we want to find the angle between 0 and pi that gives us an x-coordinate of negative 1 because we're reversing the cosine function. And so here, that happens at an angle of pi, right? Here at pi, we're at the point negative 1 comma 0, and arc cosine, or sorry, cosine of pi gives us that x-coordinate, negative 1. So arc cosine of negative 1 is going to give us pi. So here this is equal to pi. Now what about our last example? We want to evaluate cosecant of tangent inverse of 7 over 9. So that here we've got this a little bit reversed now. We're evaluating a trigonometric function at the inverse trigonometric function of 7 over 9. And so here, when we're not dealing with such nice familiar values on our unit circle, we need to incorporate triangles if we're trying to avoid using a calculator. So recall that tangent of an angle theta is the ratio opposite over adjacent. Right, so if I have some triangle here and some angle theta, and this is the opposite side, this is the adjacent side to our angle, and this is the hypotenuse of our right triangle, well, tangent of this angle gives us the opposite side length divided by the adjacent side length. And so here, if I want to consider tangent inverse kind of in the context of right triangles, the idea is that if I take tangent inverse of a ratio, and I view that ratio as the opposite over adjacent side lengths of a right triangle, it's going to give us back that angle corresponding to the angle that has those relative positions of opposite and adjacent on our triangle. So here, if I take inverse tangent of 7 over 9, this is like saying if I have an angle theta here, and an opposite side length of 7, an adjacent side length of 9, tangent inverse of 7 over 9 is going to give us back this angle. This is tangent inverse of 7 over 9. It's giving us back this angle theta. And so here, we don't actually have to compute what theta is, we just have to know that tangent inverse is giving us back this angle. And then when we want to evaluate cosecant of this angle, what we obtain from tangent inverse of 7 over 9, well, it's going to take a new ratio, right? Cosecant of an angle is, well, it's the reciprocal of the sine function. Sine is opposite over hypotenuse. Well, cosecant is the reciprocal, that's hypotenuse over opposite. And in this case, we already know what that is. We know what the we know what the opposite side length is. We just need the hypotenuse. We just need this missing side length. And we can find this with the Pythagorean theorem. Right, so if I label it, maybe instead of a question mark, let's say I label it C. So we've got that 7 squared plus 9 squared should be C squared by the Pythagorean theorem. So we get 49 plus 81 is equal to C squared, which is 130 is equal to C squared. And C comes out to be plus or minus the square root of 130. So here, I can safely say this is square root of 130. And so that makes cosecant of this angle, cosecant of inverse tangent of 7 over 9, that makes this equal to, well, this is equal to hypotenuse, the square root of 130 divided by adjacent. So this is, divided by opposite, so this is over 7. This is the square root of 130 over 7. All right, so let me recap that. So here, inverse trigonometric functions can be viewed as computing angles from the ratios of the side lengths of a right triangle. So here, tangent inverse of 7 over 9, we can view that as tangent inverse of the opposite over adjacent side lengths of a right triangle, the opposite side being 7, the adjacent side being 9. Tangent inverse is going to give us the angle whose opposite side length is 7 and whose adjacent side length is 9. And so here, if we want to evaluate cosecant of that angle, well, we just have to find that third side length and continue using this idea of trigonometric functions being the ratios of side lengths of triangles. Cosecant is hypotenuse over opposite, and once we have all three sides, we can find exactly that ratio. And so in this case, it was the square root of 130 as the hypotenuse divided by 7, the opposite side length. So here, let's go over some equations now. I've got 4 equations ready to go over. Here, let's start with these two, A and C from problem 5. So here, this first problem, part A, 4 cosine squared of x minus 1 is equal to 0. To solve this equation, we can use our ideas from solving quadratic equations. So notice if I get this cosine squared of x alone, I'll just have cosine squared of x is equal to some number, and I can take plus or minus the square root of both sides to get closer to just that cosine of x. So here, if we do that, if we get cosine squared of x alone by adding 1 to both sides, and then dividing both sides by 4, we get cosine squared of x is equal to 1/4. And if we take plus or minus the square root of both sides, we get cosine of x is equal to plus or minus, well, the square root of 1/4 is 1/2. And so this is like asking what values, what angles x give us a horizontal coordinate on our unit circle of plus 1/2 or minus 1/2. And so here, if I draw out my unit circle, and so cosine gives us the horizontal coordinate on the unit circle, and so we're really asking what angles give us a horizontal coordinate of 1/2 or minus 1/2. So here's a horizontal coordinate of 1/2. Right, that happens at any angle that lands here or lands here. And so here, this is one such angle is at pi over 3, but really any coterminal angle will also land at such a position. So if I add on any multiple of 2 pi to pi over 3, we'll get a solution. And similarly here, if I have negative pi over 3, or any coterminal angle, I'll end up at this bottom point. But that's only positive 1/2. That's only giving us angles which give us an x value or a horizontal coordinate of positive 1/2. What about a negative 1/2? Well, that would be about here. And really, angles that land at either of these 2 points on the left give us solutions to our equation. And so here that happens at, 2 pi over 3 in its coterminal angles, so plus 2 pi n. And this would be 4 pi over 3 plus 2 pi n. Or we could have written negative 2 pi over 3 plus 2 pi n. Those are really describing the same sets of values. So here x is equal to, maybe I'll write it directly below so I have some space on the right. So x is equal to plus or minus pi over 3 plus 2 pi n, or 2 pi over 3 plus 2 pi n. And actually, maybe for the sake of convenience, I'll write this as plus or minus 2 pi over 3 plus 2 pi n, right? Because if I could have also written an example, one of these bottom angles is just going backwards 2 pi radians, and then any of its coterminal angles included. So here, that's one way of writing down all of these solutions to this equation. 4 cosine squared of x minus 1 is equal to 0. So here, let's go over this next example, part C, and let's solve the equation 6 sine of x plus 5 is equal to 0. So to solve this equation, we want to get that sine part isolated. Right? It's kind of like a linear equation, but instead of x, we have sine of x. And so to get this sine of x isolated, we subtract 5 from both sides. We have 6 sine of x is equal to negative 5. And then dividing both sides by 6, we get sine of x is equal to negative 5 over 6. And so here, maybe just to draw a picture of what this is really describing, using our unit circle, here, right, sine takes in angles, and it gives out y coordinates on the unit circle. And so this is like saying we have a y coordinate of negative 5 over 6, which is really close to negative 1. And we want to find the angles, all such angles that bring us to these different positions, these two points on our unit circle. And so there are many different angles that do the job, but how can we get a hold of one of them? Well, negative 5 over 6 is not one of our special side lengths of a right triangle. And so this is not something we can do without the help of a calculator. So here we need to use inverse sine to find one such value. So sine inverse of that side length, negative 5 over 6, it's going to give us back an angle. Right, it's going to give us back actually an angle between negative pi over 2 and pi over 2. So actually, it's going to give us back exactly this angle here between negative pi over 2 and pi over 2. And when I evaluate this with the calculator, we get back negative 0.9851 radians. And so here, negative 0.9851 radians, that's one solution. But of course, we want all solutions, and so let's include the coterminal angles by adding plus 2 pi n. Now, what about these solutions here on the left? What about angles that come out to this position here? Well, here there's some symmetry involved with this unit circle. Right, so maybe I'll give a quick example. If I have an angle of theta here, well, here if I draw out theta, an angle of theta that's, if I draw out an angle that's this many radians away from 180 degrees, well, we end up with another angle with the same y coordinate, right? So here, it's just a rough sketch, but these two different locations, these two different angles have the same y coordinate. But this angle on the left, that's not theta, it's theta shy from pi radians. Right, so actually this angle here can be viewed as pi minus theta. Really, the sine function gives us the same values whether we take theta or whether we take pi minus theta. This is just always true. Sine of pi minus theta is always equal to sine of theta. This is really just the symmetry of our angles. These two angles are the same, at the same height. They're one's reflected from another across the y-axis. And so all of this to say that if we know one solution here is the angle negative 0.9851, well, we get another solution opposite our y-axis, our vertical axis, by taking pi minus this angle. So pi minus negative 0.985, so pi plus 0.9851. This is going to give us one angle in this position here. And then we'll incorporate the coterminal angles. And so those are all the solutions to this equation. 6 sine of x plus 5 is equal to 0. So let's go over two more equations here. Let's start with part D. So sine of x is equal to cosine of 2x. And so how do we solve this equation? Well, there's two things that are kind of keeping this from being an easier equation to solve. So one is that the inputs of these different angles, or these inputs of these two different trigonometric functions are different. And so here that really messes up being able to apply our algebra ideas and techniques to solving this equation. And so what we'll need to do to alleviate this is we'll need to use one of our double angle identities to get rid of this 2x. So we can't divide out 2 to get rid of that factor of 2. We can't factor out 2 because it's really in the input of this cosine function. There's no algebra that we can do to get rid of inputs. We can only use identities to deal with these inputs. And so here, what are our double angle identities for cosine that we can use here? Well, cosine of 2x is equal to cosine squared of x minus sine squared of x. It's also equal to 2 cosine squared of x minus 1. It's also equal to 1 minus 2 sine squared of x. And so which one do we use here? Well, it's preferable to have the same trigonometric function with the same input values all throughout our equation. So let's use this third identity, so our entire equation is in terms of sine. So this makes our equation into sine of x is equal to, well, it's equal to 1 minus, not just sine squared of x, 2 sine squared of x. And so now we can use our techniques from algebra. This is a quadratic equation in terms of sine. So let me try and solve using our approaches to solving quadratic equations. Let's try and factor this equation. Solve by factoring. So to do so, we would make all the terms go onto one side and then try and factor that side. So I'm going to add 2 sine squared of x to both sides. And I'm going to subtract away 1 from both sides. So now how does this factor? Well, here, I know if I want to get a 2 sine squared of x, I'm going to need a sine of x, 2 sine of x in one of my terms. And a sine of x is the first term in my other factor. And then if I want to get this minus 1 here from multiplying our two constant terms, well, I better have a plus 1 and a minus 1. And where should the plus 1 go and where should the minus 1 go? Well, I'm going to put a plus 1 here and a minus 1 here, so that when I do the rest of this multiplication, well, 2 sine of x times 1 will give us 2 sine of x. Minus 1 times sine of x will give us minus sine of x, and those will combine to this middle term here. So this is our factorization. And to solve this equation, now we need to solve the equations for when these factors themselves are 0. So 2 sine of x minus 1 is equal to 0, and sine of x plus 1 is equal to 0. So here, isolating the sine of x gives us 2 sine of x is equal to 1, or sine of x is equal to 1/2. And then on the other equation, subtracting 1 from both sides gives us sine of x is equal to negative 1. So let's solve this equation on the left. If we draw out the unit circle, we're looking for angles that lead to a y coordinate of 1/2. Right, so here's a y coordinate of 1/2. Any angle that brings us to either of these two positions is going to be a solution angle. And so one such angle is pi over 6, but of course its coterminal angles are also solutions. Whereas another angle is 5 pi over 6, and its coterminal angles. Right, so here, really these are just angles that are 30 degrees shy or 30 degrees away from the x-axis or the horizontal axis. And so here we get a 30, 60, 90 triangle with really the height of these triangles as 1/2, the short side length of the triangle. Okay, so those are solutions to this equation, which means that they're solutions to our original equation, but they're not all of the solutions. We also need to solve this equation here. And so here we want to find angles which give us a y coordinate. Right, sine gives us y coordinates on the unit circle. So here we're finding angles that give us a y coordinate of negative 1. And so there's the y coordinate of negative 1 on my unit circle. It's at the very bottom. And the angles that do the job here are, well, really they're 3 pi over 2 is one such angle. And any coterminal angle. Right, so plus 2 pi n. And so really our solutions to this first equation are x is equal to, well, pi over 6 plus 2 pi n, 5 pi over 6 plus 2 pi n, and then we just said 3 pi over 2 plus 2 pi n. So these are all the families of solutions, all of the solutions between 0 and 2 pi, along with their coterminal angles. So let's go through one more example in this equations problem. Here we want to solve this equation, cosine of theta times cosine of 2 theta minus sine of theta times sine of 2 theta is equal to -1. And so this looks a lot like one of our angle addition or angle subtraction identities. So we have the angle addition identity for cosine is cosine of u plus v. Oh, I should use green here. This is equal to cosine of u times cosine of v minus sine of our first angle, sine of u, times sine of v. And so here notice that, well, we've got exactly that. We've got cosine of some angle times sine of another angle, take away sine of that same first angle times sine of that same second angle. And so really this is equivalent to, this left-hand side is equivalent to cosine of that first angle plus that second angle. Right, if you were to expand out this expression using the cosine angle addition identity, we would obtain the same expression on our left in this side, or on the left side of this equation. And so we're saying that this left side, well, it's going to be equal to the right side. We want to find when it's equal to the right side, when it's equal to -1. So we're solving this equation. Cosine of 3 theta is equal to -1. And so when we have this equation where the input is different than just a single variable, solving it gets a little bit trickier. And so one technique we can use is we can use sort of substitution idea. We can just momentarily rename 3 theta u. Just represent 3 theta with this variable u and solve a new equation. And we just have to keep in mind that u represents 3 theta. So let's solve cosine of u is equal to -1, and then work our ways backwards to find solutions in terms of theta. So what are the solutions to cosine of u is equal to -1? Well, here, cosine gives us x coordinates on the unit circle. So this result of cosine of u is going to be an x coordinate. And when do we have an x coordinate of -1 on the unit circle? Well, it's all the way on the left. At this point, -1, 0. And so what angles, what values of u do the job here? Give us an x coordinate of -1, we'll add an angle of pi, or if we add on 2 pi on top of that, so 3 pi, or another coterminal angle if we were at 5 pi. Well, these are all examples of solutions to this equation. Really, u is equal to pi or its coterminal angles, right? Pi plus 2 pi n. These would be solutions to this equation, cosine of u is equal to -1. But again, we're not trying to really solve this equation. We want to solve the equation cosine of 3 theta is equal to -1. And so remember that here 3 theta and u, they're the same thing. So I'm going to reverse my substitution here. I figured out what u ought to be. Now what does that tell me 3 theta ought to be? Well, 3 theta is the same, pi plus 2 pi n. Right? 3 theta and u, they represent the same thing. And so if I want theta, well, I'm going to divide both sides by 3 to get that theta is equal to, well, dividing both sides by 3 means dividing each term by 3. So we've got pi over 3 plus 2 pi n over 3. Now these are the solutions to our original equation. And they're the solutions to cosine of 3 theta is equal to -1. So let's use identities now to figure out the values of d and e. And so here, just like the previous problem, this identity here, or sorry, this expression, looks like the result of an angle addition identity, but this time for sine. All right, so sine of u plus v, well, this is equal to sine of u times cosine of v, the second angle, plus cosine of the first angle, times sine of the second angle. And that's exactly what we have here, where the first angle is 5 degrees, and the second angle is 40 degrees. And so we can sort of reverse this and recognize that it looks a lot like this right-hand side. And this equality goes both ways, so we can rewrite it sort of in this form of this left-hand side, that really it can be expressed as sine of 5 degrees plus 40 degrees. Well, this is the same as sine of 45 degrees, and we know what this is, right? Sine of 45 degrees, if we draw out our unit circle, 45 degrees is, well, right between 0 and 90 degrees. Here we get this 45, 45, 90 triangle, and the y-coordinate on the unit circle here is the square root of 2 over 2. Okay, what about this expression here for part E? Well, this is from the cosine double angle identity. So one of the double angle identities for cosine is cosine of 2x is equal to cosine squared of x minus sine squared of x. And so in this case, we're saying that x here, that's exactly pi over 8. So we have this expression on the left where x is pi over 8. We can rewrite it in terms of the expression on the left. Sorry, did I say left earlier? So we have this cosine squared of pi over 8 minus sine squared of pi over 8. It's identical to our expression on the right. We can rewrite it in terms of the expression on the left, cosine of twice that angle. So here really this is the same as cosine of 2 times pi over 8. Well, that's cosine of pi over 4. And so what is cosine of pi over 4? Well, here it's this side length in this picture, this horizontal side length, and that's the square root of 2 over 2. Okay, so here let's go through this problem. We're given that cosine inverse of negative 3 over 4 is equal to theta. And we want to sort of answer a handful of different problems in terms of sine of theta and cosine of theta. Now, recall that cosine inverse is going to take in a side length, an x-coordinate, and it's going to give back an angle. And we said that cosine inverse only gives back angles between 0 and pi. So when we look at these x-coordinates of negative 3 over 4 on this unit circle, usually there's multiple angles that do the job. Cosine is only going to return the angle here between 0 and pi radians. So here, this is exactly the angle, theta. And here, again, just to make this very clear, this is x is equal to negative 3 over 4. So here we're just asked to sketch our angle, and now we need to figure out the x and the y coordinate of this point on our unit circle. Well, we've already found the x coordinate, just the way we've constructed this picture here has an x coordinate of negative 3 over 4. And now how do we find the y coordinate? Well, this circle is given by the equation x squared plus y squared is equal to 1. All the points on this circle satisfy this equation. So let's plug in negative 3 over 4 for x to figure out y. And so this gives us 9 over 16 plus y squared is equal to 1. Subtracting 9 over 16 from both sides gives us 7 over 16. And so y is equal to plus or minus the square root of 7 over the square root of 16, and the square root of 16 is just 4. So is it plus or is it minus? Well, here, if it were minus, it would be this point down here, right? This point has a negative y value. It's below this horizontal axis. And points below the horizontal axis have a negative y coordinate. Well, this point is above the y or the x-axis, so it has a positive y coordinate. Here we're looking at plus square root of 7 over 4. Now we want to evaluate sine, cosine, and tangent of theta. Well, sine, cosine, and tangent, sine and cosine, those are the y and x coordinates respectively of our point. So if this point is negative 3 over 4, comma, square root of 7 over 4, well, here that makes sine of theta equal square root of 7 over 4. And that makes cosine of theta, well, negative 3 over 4. And tangent of theta is the ratio of these two. square root of 7 over 4 divided by negative 3 over 4. And so I can clean that up as square root of 7, negative square root of 7 over 3. So that's tangent of theta. All right, what about sine, cosine, and tangent of negative theta? Well, I mean, you can draw out the picture here and see that negative theta would be down here, and you can kind of figure out that instead of having this point, we would have the same point, but with a negative y value. And so that's another way of seeing how the identities, the negative angle identities, look for our sine and cosine and tangent functions. So sine of negative theta, it's always equal to negative sine of theta. If we negate the input, we negate the output. And you can kind of see it in this picture here. If I instead go clockwise around my circle, well, I'm going to have the opposite y value. Similarly, if I have tangent of negative theta, if I negate the input of our tangent function, well, we get the opposite slope. And then the cosine function, well, if I go clockwise around this unit circle as opposed to counterclockwise, well, that doesn't change the x value on this unit circle. We actually get the same thing. Cosine of negative theta is the same as cosine of theta. So all this to say that sine of negative theta is negative sine of theta. This is negative square root of 7 over 4. Cosine of theta is equal to, well, it's the same as cosine of negative theta. And so here this is negative 3 over 4. And then tangent of negative theta, here this is going to negate the output. This is the square root of 7 over 3. So here, for this next example, sine of theta over 2, this requires using the half angle identity. This is plus or minus the square root of 1 minus cosine of x over 2. And cosine of theta over 2, this is equal to plus or minus the square root of 1 plus cosine of x over 2. And so we already know cosine of x. We've figured out cosine of x, and so we can evaluate these without too much difficulty. This is equal to plus or minus the square root of, well, what's cosine of x? Cosine of x is negative 3 over 4. This is 1 minus negative 3 over 4, so that's 1 plus 3 over 4 all over 2. So this is plus or minus the square root of, well, 1 is 4 over 4, so this is 7 over 4 over 2, which is square root of 7 over 8. And so here, I'm not going to make you really go through so much of the motions of simplifying this right now, just also to save us some time. Let's just leave it as the square root of 7 over 8. But one thing we do have to do is we have to decide whether we've got a plus or a minus here. Well, here, if we look at our angle in our picture above, our angle theta, let me just remove a little bit of the clutter. Well, what would theta over 2 look like as an angle if we cut this angle in half? Well, it would fall somewhere in this first quadrant, right? Any angle in the second quadrant, if we cut it in half, it's going to be in the first quadrant. I don't know exactly where it's going to be, but I know it's going to be in the first quadrant. And everything in the first quadrant has a positive x and y coordinate. So I know here, if this is theta over 2, well, I know sine of theta over 2 is going to be greater than 0, and I know cosine of theta over 2 is going to be greater than 0. And so here, when we say plus or minus the square root of 7 over 8, really, in this case, it's plus. Even without knowing the exact value of theta, we know that it's in the first quadrant. We know sine is going to be positive. And similarly here, we're going to get plus a positive value from our cosine half angle identity. This is the square root of 1 minus 3 over 4, right? 1 plus negative 3 over 4. This is the square root of, well, 1/4 over 2. This is the square root of 1 over 8. So maybe let me just leave it at that. Here, let's evaluate sine of 2 theta. Well, that's based on the double angle identity for sine. That's 2 times sine of theta times cosine of theta. And so earlier we saw that sine of theta, this was square root of 7 over 4. Cosine of theta, this was negative 3 over 4. And so this comes out to be negative 2 times 3 times the square root of 7 over 16, which is negative 3 square root 7 over 8. What about the cosine double angle identity? So here we've got cosine of 2 theta that we want to figure out. There's many different ways we can do this. There are 3 different identities for the double angle of cosine. So this is cosine squared of theta minus sine squared of theta. 2 cosine squared of theta minus 1, and 1 minus 2 sine squared of theta. We can use whichever one we like. We know sine, we know cosine. It doesn't. Each one has equivalent difficulty, but maybe let me use this example here. I think it's just friendlier to use just one of these values instead of having to use both. And so here in this case, cosine of 2 theta, this is equal to 2 times cosine squared of theta. Well, cosine of theta is negative 3 over 4. We're going to square that and subtract away 1 after doubling it. So this is 2 times 9 over 16 minus 1. This is 9 over 8 minus 1. This is 1 over 8. Right, so if I subtract away 8 over 8, I'm just going to be left with 1 over 8. And so the last thing we want to do is we want to evaluate sine of theta plus pi over 6. And this requires using the angle addition identity u plus v. Sine of u plus v is equal to sine of u cosine of v plus cosine of u sine of v. And so in this case, we have sine of theta plus, sine of theta times cosine of pi over 6 plus cosine of theta plus, times sine of pi over 6. Well, this is equal to, well, we know sine of theta is square root of 7 over 4. We know cosine of pi over 6, that's square root of 3 over 2. We've got cosine of theta is negative 3 over 4. And we've got sine of pi over 6 is 1/2. So this is square root of 21 over 8 minus 3 over 8. And this doesn't really come out much better. This is negative 3 plus square root of 21 all over 8. So here let's go through an example where we want to evaluate sine of x over 2, cosine of x over 2, and tangent of x over 2. So we already went through a similar example in the previous problem, but this is a little bit different. This time we're given cotangent of x, and we're given the fact that it's an angle between 180 degrees and 270. So here, recall that sine of x over 2, this is equal to plus or minus square root of 1 minus cosine of x all over 2, and then cosine of x over 2, this is equal to plus or minus the square root of 1 plus cosine of x all over 2. And then if we want to find tangent of x over 2, we just take these two values and divide them from one another. So here, cotangent of x is equal to 5. Maybe we can use the help of a triangle here. Right? So here, if I draw out my unit circle, we're saying that this is x is going to be an angle between 180 and 270. So it's going to be in this quadrant here, quadrant 3. And here there's some angle x. Maybe I'll just draw some random angle just to have some sort of picture here. But there's sort of a triangle at play. And we're saying that this angle x, when we take cotangent of it, in other words, we take the adjacent side length and divide it by the opposite side length, we end up with 5. And so maybe let's really draw this picture out. Sorry, my screen keeps messing up. Let's draw this picture out off to this side. So here, we've got our angle x. And we say that when we take cotangent of this angle, we take this ratio opposite over, sorry, this is opposite. We take adjacent over opposite, right? Cotangent of x is equal to opposite over adjacent. Cotangent of x is equal to adjacent over opposite. we're saying that we're getting the ratio 5 here, so I can think of this as 5 over 1. And so I can kind of do what we did before for our, when we dealt with inverse trigonometric functions. We can view this ratio 5 over 1 as the side lengths of this right triangle, 5 and 1. So actually maybe let me, oh actually no, sorry, I keep messing this up. Cotangent is adjacent over opposite. So here I've got 5 as my adjacent side and 1 as my opposite side length. And so here, if we can figure out cosine of x, then we've finished our problem. We can evaluate sine of x over 2 and cosine of x over 2. So if we can get cosine of x from cotangent of x, we're done. And now cosine of x, this is going to be adjacent over hypotenuse. And well, adjacent, we've got it already here. It's going to give us 5. And then we just need the hypotenuse. And this is going to come from the Pythagorean theorem, right? So the hypotenuse, I call this c. Well, c squared is equal to 1 squared plus 5 squared. So here this is 25 plus 1. This is 26. So c is equal to plus or minus the square root of 26. And that doesn't really clean up, I don't think. So I'm just going to leave it like that. So c is the square root of 26 in this picture. And so let me fill that in here. So maybe for a moment, if we're going to use this triangle, let's not consider this in terms of the unit circle. Let's think of this as a circle of radius, the square root of 26. Right, then this horizontal position is 5. In the negative direction, that makes it negative 5. And then this vertical coordinate position, this is 1 in the negative direction. This is negative 1. Okay, so here that makes cosine of x. Well, it's going to take this adjacent side divided by the hypotenuse, and so cosine of x is going to give us negative 5 over the square root of 26. And maybe I'll rationalize this. Now this is 5 square root 26 over 26. So that's cosine of x. And so if I want to evaluate sine of x over 2, I just need to plug that in. So here's sine of x over 2. It's equal to plus or minus the square root of 1 minus cosine of x all over 2. And so this is equal to plus or minus the square root of 1 plus 5 square root 26 all over, well not all, just over 26 on the second term, and then all over 2. So 1 is the same as 26 over 26. And so this comes out to be 26 plus 5 square root 26 over 26 all over 2, which makes the denominator 52. And so if we take, we know that our angle is in quadrant 3. And if our angle is in quadrant 3 and we look at x over 2, or half this angle, well, we know that half of this angle, maybe just to speak very broadly, it's going to end up somewhere in this top half. Right, this angle is between 180 degrees and 270 degrees. And if we take half of that, well, we're going to end up between 90 degrees, and so actually maybe I'll erase this. We're going to end up between 90 degrees and 135 degrees. So we're somewhere, half of our angle is somewhere in here. X over 2 is somewhere in this region here as an angle. And so sine of x over 2, sine of the angle that ends up here, is because it's above the or the x-axis, it's going to be positive. Sine of x over 2, this is positive. Now if we look at cosine of x over 2, well, we're going to be on the left side of our y-axis. We're going to be in the negative x coordinate positions, the negative horizontal coordinate positions, and so cosine of x over 2 is going to be negative. So if we go through the same motions, but for cosine, this is going to be negative. So here we have plus or minus the square root of 1 plus cosine of x, all divided by 2, and cosine of x over 2, it's going to be negative. So this is negative the square root of 1, what is this, 1 minus 5 square root 26 over 26, all divided by 2. Actually, let me leave it like this. So here, let me just leave this answer like this so we don't spend too much time really going over the real details of this problem that I think are just a little on the excessive side. As long as you understand how to determine the sign, positive or negative of this trigonometric expression, and as long as you know how to get to the bottom of this, the value of this trigonometric expression, then I am content. So one thing we haven't done is we haven't evaluated tangent of x over 2. Our values are pretty messy here. I think when it comes to a problem on the test, I wouldn't give you something so messy. So I think just maybe for the sake of time, let's not evaluate tangent of x over 2. Just know that you would take your sine value and divide it by your cosine value. So let's go over one last example here, and let's find all of the possible triangles satisfying the conditions in part A. Right, so here we have a side length and its opposite angle. So here I have my angle 58 degrees. I've got a side length of 82, not opposite 58 degrees, and then I've got a side length of 73 that is opposite our angle. So here we've got angle B, side C, angle C, so that makes this angle A and this angle A. And so how do we find the missing values in this triangle? Well, we can use the law of sines, right? So law of sines says that if I take sine of some angle and its opposite side length, this is going to be the same as the sine of another angle and its opposite side length divided by its opposite side length, which is also equivalent to sine of the last angle divided by its opposite side length. And so here we can, as long as we have 3 out of 4 of any of these pieces, like in any pair of these parts of the equation, we will be able to solve for the fourth. And so here, maybe just to really show an example of that, we have an angle and its opposite side length. Right? Sine of B is sine of 58 degrees divided by B is 73. And so we can use this to figure out, sine of C over C, right? So sine of C, we don't have the angle C, but we do have the side length C. We do have 82 here. And so if I want to solve this equation for C, to get that angle, that missing angle, well, I need to get that sine of C alone. This is accomplished by multiplying both sides by 82, giving us 82 sine of 58 degrees over 73. That's what sine of C is equal to. And so when we evaluate this in a calculator, being careful to use degrees mode, since we're given an angle in degrees, this gives us approximately 0.9526. So that's what sine of C is equal to. And we want to figure out the angle C that do this job, that makes sense for a triangle. And so if we draw out our picture like we have been when we've solved trigonometric equations, right, saying that sine of C is equal to 0.9526, this is like saying we've got a y coordinate of 0.9526. What angles lead to these y coordinates? And that's not a nice angle. We don't know it without using inverse trig. And so we can use inverse trig to get one such angle. And so inverse trig is going to give us back the angle between negative 90 and positive 90 degrees. Of course, this doesn't mean that other angles don't work. This is just the only one that inverse trig is going to give us. So this angle here, this is going to be arc sine, or sine inverse of 0.9526, so on, so on, so on. You want to use as many decimal places as you can to get the most precise answer or value possible. But this would give us, this gives us approximately 72.29 degrees. And so here, what happens when we use this angle for C? Well, then we can use the fact that all the angles sum to 180 degrees to get this missing angle here. So this would be 49.71 degrees, because that's what it takes to add them all up together and get 180 degrees. You can figure this out by subtracting away our two known angles to get this last third angle. And then here, maybe just for the sake of time again, let me not go into computing A, the side length A, but you could use the law of sines again. Here we would have these three pieces of information, we'd just be missing A, so we could solve for A. But now let me go back to this picture here. So we said that there's another angle that could possibly work, that would fit for this angle C. And so again, earlier we said that sine of pi minus theta is always equal to sine of theta. And in degrees, this is expressed as sine of 180 degrees minus theta is equal to sine of theta. And so we have to check this value of an angle to see if it makes sense to plug into this triangle. And when we take 180 degrees minus this angle, theta, 72.29, what we get here is that this angle is approximately 107.71 degrees, right? 72 degrees shy of 180 degrees. And so here, if we try and fit this into sort of a triangle with the same information we were given to the start, this is 58 degrees, this is 82 as a side length. What we end up with is, here we end up with this angle C is 100, and I should do this in orange, 107.71 degrees. And so this side length this was 73, I believe. This is angle A, side length A, angle B, side length B. And so with that angle, we end up with this angle is 14.28 degrees when we try and add them all up to make sure that they end up being the total 180 degrees. And so this triangle works. It's a valid triangle. And so there's two triangles here that satisfy the given conditions. And really, the fact that there were two triangles came from this fact that these two angles satisfy our sine equation. Sine of C is equal to 0.9526. And in addition to that, when we try and fit them into the triangle, we can find three angles that sum to 180 degrees. Sometimes we'll get angles that when we try and do this, they sum to more than 180 degrees, and then that's telling us that there isn't such a triangle, there isn't such a second triangle here. But in this case there is, and so just be aware that you have to check for all possible triangles sometimes.